Welcome everyone, this is Sandy Andrew, your host of the Universal Learning Series radio show, where we discover the spiritual and scientific universe. We are broadcasting live from the land of the free, the United States of America. Our topic of discussion this week is Widom Larsen theory with Louis Larsen. Are we on the verge of an energy revolution that will solve the current worldwide energy problem while dramatically lowering climate pollution? Louis Larsen, the president of Lattice Energy LLC, seems to think so. The Widom Larsen theory explains low-energy nuclear reactions at ordinary temperatures and pressures. Unlike conventional neutron-triggered fission and hot fusion reactions that involve random collision of individual particles and require extremely high temperatures and pressures, which equates to perpetual danger, the Widom Larsen theory proposes collective processes involving many particles acting in concert to generate neutrons with negligible kinetic energies, i.e., they have ultra-low momentum and are not as harmful as such generated by current nuclear energizing methods. Deadly energetic neutrons and X-ray gamma radiation are typically produced by nuclear fission or hot fusion reactions. However, the charged particle products produced by LENRs, that is, low-energy nuclear reactions, cannot penetrate a piece of paper or the human skin. While still being nuclear energy in principle, LENRs have intrinsically huge advantages over any chemical power generation technologies with regard to energy density. Chemical reactions can release stored electronic energy on the order of several electron volts. Nuclear reactions can release stored nuclear binding energy on the order of mega electron volts, which is more than 1,000,000 times larger than typical chemical energies. Repeat that again, which is more than 1,000,000 times larger than typical chemical energies. This creates a potential commercial opportunity to develop cost-effective LENR portable power sources that have unprecedented performance in terms of system energy density and longevity. Can this science, which has been reviewed by many in the field, including NASA, change the world on an immeasurable scale? You listen, you decide, and we would like to welcome Louis Larsen to the Universal Learning Series radio show.
Hi, Sandy. I'm delighted to be here.
Thank you, Louis. Good afternoon to you, sir. Let's start with nuclear energy as a whole. So many of us relate to nuclear energy as two things. One, nuclear submarines, which can blow the planet to bits. Number two, power stations with a huge ball on it. If they melt down, poison everything around it, okay? That's most people's take, and I'll speak humbly on this and naively, most people's take on nuclear energy. I would hazard a guess that a lot of us don't really understand the general principles of nuclear energy. Can you describe in principle what nuclear energy is for us, Louis, please?
Yes. First, I'd need to describe what an atom is. An atom basically is comprised of these outer electrons swirling around, and then you have a nucleus way inside there, a small nucleus, where you've got protons and neutrons. Mm-hmm. When you look at the processes that we typically use, besides the ones you mentioned, fission reactions and fission reactors in submarines, typically what we're doing is we're manipulating electrons. We bring electrons up to a higher energy level. They, let's say, through a current path, flow down to a lower energy level, and we can harvest stored electrical energy. And we can make electrical energy with magnetic induction. nuclear energy, as Sandy said, is much larger, where you have EVs messing around with electrons. Once you go into the nucleus, the scale of energies goes way up. Now, the existing technologies that we're familiar with, Sandy just mentioned fission. You've also heard fusion, maybe in the initial context of a fusion bomb, and now we're talking about these fusion reactors that the ITER that they're working on in France. Well, these nuclear technologies are based on a type of interaction that occurs in the nucleus. Is called a strong interaction. And with a strong interaction, you get these nasties. You get radioactive isotopes, you get energetic neutrons, and you get hard X and gamma radiation. There's another kind of nuclear process called a weak interaction. And the weak interactions, what happened, let's take our nuclear technologies today, they really all grew out of the weapons programs. In World War II, everybody was afraid that the bad guys would get the bomb first, and so there was the Manhattan Project in the United States, and then nuclear weapons came into being. The fission technologies we use in our reactors today, whether they're in submarines or in power plants, all effectively came out of the weapons programs. Now, Enrico Fermi, who was one of the chief architects of the Manhattan Project, was able to explain weak interactions in the 1930s, and in fact, he got a Nobel Prize for it. But in all the hullabaloo in developing nuclear weapons, weak interactions kind of went to the side. Everybody forgot about them. Fermi died just after World War II, so he didn't live very long to go back to his old love, which was the weak interactions. And scientists basically thought that it wasn't anything you could do power generation of any kind with. Well, that's not the case. An overall theory of weak interactions at a very high level at high energies was developed in the 60s by Glashow, Salem, and Weinberg. And they got a Nobel Prize for it, but it wasn't really experimentally verified until the 80s. So when a former subject called cold fusion now erupted in 1989, people were confused. They thought they were looking at a strong interaction process. It wasn't. It was weak interactions. Does that answer your question?
Well, it gives a general understanding of nuclear energy. Thanks, Louis. Let me talk a little bit about cold fusion. Is cold fusion related at all to the Widom Larsen theory?
It is. In fact, it's not fusion. What happened is back in 1989, these two very talented electrochemists, Pons and Fleischmann, had this, at the time, it was rational in some way, but a slightly cockeyed theory that they could induce fusion reactions inside metals that were formed the hydrides, and all a hydride is a metal that will suck up hydrogen inside, just like a sponge sucks up water. So they did have some logic to what they were doing, and they saw a lot of heat. They even saw a little bit of helium, and you can't make helium with a chemical process. So they said, aha, we've got deuterium in this cell. We see helium. Ergo, it must be fusion. Well, they were wrong. They were speculating, they were grandstanding, and they were essentially drummed out of the scientific community. The other problem that existed was because they really didn't have a working paradigm or a real theory for what was going on, the experiments couldn't be reproduced. In fact, they're still difficult to do, primarily because at the time, meaning 1989, nanotechnology as it exists today didn't exist. So the technologies weren't even available then to develop it if they had a theory.
So, Louis, to be clear on this, for the benefit of the audience here, cold fusion is a little bit related to Widom Larsen theory, but it's not the same thing. We're not talking about Widom Larsen theory when we talk only about cold fusion. Am I correct in that?
The phenomena called cold fusion by people in the field and the press is not fusion. It is a real nuclear phenomena, but it's based on primarily weak interactions, not strong interaction fusion. And so you have a whole body of over 20 years of these nuclear effects that many people in the field or people outside called cold fusion, which in fact were nuclear, but aren't fusion. Never were.
Interesting. Okay. Well, now let's move on to the Widom Larsen theory. Let's talk about this for a few minutes. Can you describe the basic principle of how your theory works to generate energy?
First, I'll step up to a very high level, then I'll step back down to a lower level, just so you can see the big picture, and then I'll drop back.
Okay.
What's different and unique about what we did, there's no new physics of any kind in our theory. None. Nada. What we did is we took existing physics and put it together in a novel way. And in particular, what we did was we took the weak interaction, and a weak interaction is any type of nuclear process which either emits or absorbs a neutrino. And let me just digress from a neutrino is a photon. It's sort of like visible light, but unlike visible light, neutrinos don't interact much with ordinary matter. I mean, there are billions of neutrinos passing through our bodies right now from the sun with no ill effect. So when you have these weak interactions, neutrinos are involved. Now, in the case of LENRs, typically you're emitting neutrinos. And the other piece that we put together, what are called collective effects. Now, the difference between fusion, let's say, as people think it happens in stars, and certainly how it happens in a fusion weapon, is that you get these two particles at very high energies, which means it's really hot. And a small percentage of them slam together head-on, and if there's enough energy, you've got two sets of plus charges in these nuclei, so just like magnets of the same polarity repel each other, it's called a Coulomb barrier because you've got to get through that before the strong nuclear force can suck all these things into a nucleus. So in the case of weak interactions, you don't have a Coulomb barrier. Now, let me go to weak interactions. So what we have is in weak interactions, you can add up energy across a large number of particles. So no individual particles in general don't have huge energies, which means it's not hot. So when you combine collective effects and the electroweak theory, that's part of what's called the standard model of physics, you get what we've done, and that is what we put together. Now, here's what it means in a practical sense. In a chemical cell, which is like a Pond-Fleischmann cell, which is sort of like a battery. You've got an electrolyte, you've got an anode, a cathode, and you run a current through it. And of course, there's hydrogen in it. In this case, they had deuterium instead of regular water, which is all deuterium is that's a hydrogen atom with one more neutron added. And when you have that situation, you can have these weak interactions take place. Now I'll say what happens in the cathode. So in their case, in their old experiments, they had a platinum anode and a palladium cathode, and they ran a current through. Now, when you're doing that, you're splitting water, you're loading hydrogen into this, in this case deuterium, into a palladium lattice. And these lattices are like sponges. If you ever take a dry sponge and put it under your tap and go drip, 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 eventually it becomes saturated. When it does that, you see little droplets on the surface. The same thing happens in a metallic hydride and happened in their cells. And so when you do this, and it's called loading the hydride, so the thing gets saturated with either hydrogen or deuterium, these little places, little drops, so to speak, of these things appear on the surface. Well, these drops are a whole patch, a little, call it a circular patch, say 30 microns, which is pretty tiny. It's smaller than the end of a pin, with thousands of these protons or deuterons in it. Well, what's interesting is on metals, there's a film of electrons on the surface of metal that all oscillate together. They're called, fancy name, surface plasmons. Then you have these little droplets of these protons or deuterons that form in those little patches, just above them, nowhere else, but in these little random droplets. There's a coupling that occurs between the electrons, which are a minus charge, and the protons, which are a plus charge, and this fancy thing called Born-Oppenheimer approximation breaks down. That's just a very technical way to say that these protons, which weigh an awful lot more than the electrons, through the electromagnetic field, grab them and shake them back and forth. Well, according to what that does is it creates these neutrons, which are a reaction between an electron and a proton, or an electron and a deuteron, which makes this big neutron, which is absorbed. You don't see it. And the heavy electrons, which are also there, absorb the gammas and convert them to infrared. So that's the whole story in an electrolytic cell.
Okay. What would be the benefits of this type of energy production, Lewis, in terms of the everyday man, woman, and child here on Earth? What would be their benefits? What would they see if this type of energizing equipment was produced on a mass scale?
If it's successfully commercialized, and that step is ahead of the field, I mean, there's a lot of hard engineering to do, but assuming that's gotten through successfully, and obviously I think that can be done, what it would mean is, given that you don't have energetic neutrons, given that you don't make these nasty gamma rays, and given that you don't make radioactive isotopes, you don't need shielding, and you don't need containment. In other words, there's no nasty long-lived waste to deal with. So what does that mean? Well, if you take a typical fission reactor, like you have a number of them scattered around the country and a group of them here in Illinois, you've got 3 feet of concrete and a foot of steel between the core of that reactor and human beings around the outside. Well, in this case, now you're doing fission, which releases a couple hundred of MeV. In the case of these weak interactions, you can release up to, say, 20 MeV, which is, about 10%. But the good news is you don't need shielding, you don't have to worry about waste, and you can do it under mild conditions, which means that you can do small devices that aren't shielded, which in early incarnations would look a lot like batteries. I mean, you got batteries, and we all use them in our electronic products. And if you had a battery in your, say, laptop that lasted 500 or 1,000 hours, or maybe even longer than that, it would be a good thing. So because you don't need shielding, you can build potentially portable products with this, and they will scale. In other words, if you can build the little stuff, and you use nanotechnology in an analogous way to the way they use processes in the electronics industry. So in the electronics industry, you started out in the late 60s, early 70s, and they were using big die sizes and large featured things on the surface of these microprocessors. And over time, and with manufacturing, you have these wonderful, they call them the experience curve, and the more you make, the cheaper they get. The same would likely be true of LENRs. So if you have LENR devices and you build a lot of them, they get cheaper and cheaper and cheaper, and they'll scale. For example, back in the early days of computers, you remember, if people remember the little IBM PC that had, I think it was an 8 megahertz processor. Now, in our PCs, we have more power in a PC at home than you had in mainframes 20, 30 years ago. And in addition, mainframes today don't have specialized specialized large processors. It's a bunch of commodity microprocessors like you use in your PC. That's what Google uses. They don't use mainframes. So, by analogy, if we can do this, and if nanotechnology is employed, and it will scale, it gets cheaper, it scales higher, and because the fuels that we use here, you can use nickel, you can use titanium, you can use lithium, and you release millions of times more energy. In theory, if we can do this, we'll collapse the cost of energy. We'll democratize access to energy. It will be cheap and affordable the same way that computers and software become cheap and affordable by everybody. That's the goal.
let's recap a couple of things here. Number one, you're saying that this form of low nuclear energy is going to be clean. It's not going to be dangerous.
Yes, sir.
Number two, you're saying it's going to be a lot cheaper to produce energy with these devices long term.
Yeah, initially it wouldn't, but in the long term, yes, it would.
Yes, I mean, that's standard economics. Now, number three, you're talking about utilizing less resources from the planet, less raw materials, less fuel to make the energy, correct?
Absolutely.
Okay, so we got a form of nuclear energy which is very clean and very safe.
Oh, and we don't produce carbon.
Bingo.
No carbon emissions.
Bingo. It's going to be very, very cheap in the long run. And then number three, it's not going to draw on the Earth's natural resources. Some, but nowhere near to the extent that we're drawing on today.
Oh, probably a factor of a million.
Jeez, that's considerably less, Lewis, by a long shot.
I'm not kidding.
No, and actually that reminds me, I think I said it at the beginning of the show during the segment, so I said it first, so there we go. Now, this could revolutionize the world in simple ways, such as pumping clean water to African villages, for example. It's okay to build pipes, right? But how do you pump clean water 700 miles across the desert?
Absolutely.
Could this help out with that problem?
Absolutely. If you look at the public health situation in rural areas of Africa, one of the biggest issues is clean water, and it's because they're using surface water. If you can have enough electricity just to drill a well and pump from a deeper well, public health is dramatically improved. And I'd like to give one more statistic. In the world today, there are 1.6 billion people that don't have any electricity. Nothing. If we can do this, and I mean the collective we, not just Lattice, and if we can roll this technology out and get it that cheap, what that means is we bring 1.6 billion people. So this is not just for the rich industrialized countries and their toys and their iPods and their portable devices. If we get this cheap enough, everybody can afford it, and we bring almost 2 billion people into the 21st century. They can have internet access, local cell phone handsets. The world changes.
You know, one of the key fundamental things I think, Lewis, on a fundamental level throughout the world is that we don't have enough people that are educated in terms of each other's culture, knowledge, history, science especially. And I believe that is a lot of the root problem of terrorism and hatred and all sorts of nasty things in the world today is the fact that people are deprived of basic things, clean water, food, electricity. How can you expect anyone to understand you or learn and grow if they don't even have clean water and don't even have a light bulb?
Absolutely. I mean, again, in theory, if this can be done, we could develop, and I mean the collective we, portable systems that you could either bring on a flatbed truck or airdrop from, bring from by helicopter into villages, where you would have a crank-up cell phone tower, local handsets, satellite connectivity to the internet, and enough extra power to run some lights and clean water. I can't imagine anything more important we could do for the human condition and solve some of the problems that you just mentioned.
Indeed.
If people aren't starving, and if they aren't being murdered in these internation tribal wars and things like that, it would be a better world.
Indeed. Why would any institution, government, or organization in the world not want to review such a scientific theory? And, well, you're also on the verge of building prototypes that could really revolutionize the energy in the world, which is our number one problem. Well, it's certainly on an economic and financial scale. Now, let's talk some more about the theory here, because you've got this theory that has been reviewed by many over the last couple of years, including NASA.
Yes.
Correct?
NASA spent over a year doing due diligence. They had a senior physicist and some others dig through all this. We worked with them to walk them through this. And you can find it on, if you go on the web, you can find it. Just search Zawodny, NASA, Widom Larsen, and their report will pop up. And the bottom line is they concluded that the physics are correct, and that's what is left is engineering. Some three-letter agencies in the government have done the same thing, and they concur with our assessment. In addition, a very, very large Japanese company, I can't mention it, I apologize I can't mention it publicly, but they have looked over our stuff, and they have concluded that our theory explains all of their experiments and everybody else's. Unfortunately, they're a competitor, so I can't tell them too much, but so there's a growing assessment that this is correct. And by the way, we did publish the core of our theory, at least in condensed matter, in a very prominent physics journal, the European Physical Journal C, Particles and Fields in 2006. And we have other publications since, part of the problem with acceptance of this, forgetting about all the cold fusion nonsense, that's the baggage of the field, it's intensely interdisciplinary. To crack this, we had to use some things from chemistry, from surface physics, from nuclear physics, from quantum electrodynamics, collective effects. It's at the intersection of a lot of disciplines, and that's why this resisted so long. So yes, there have been some very prominent parties that have looked at this, and so far nobody's found any fatal flaws in what we've done. I mean, we certainly have a lot of detractors, people that like to throw stones at what we're doing. You can get on the internet and find all that. But no one has shown that our physics or our mathematics are wrong, because they're not.
Well, I think if you're saying that NASA has looked at this in detail and has basically...
Well, they're going to be doing experiments.
Really?
Yes.
Wow. And also,
but they didn't want to give us money. I don't quite know why that was. But they're going ahead and they're going to do their own experiments. I mean, we've got, and actually what I wanted to point out to the audience too is this doesn't just go back to 1989. Once we did our sort of, called it the Widom Larsen theory, the unified theory, if you will, of the LENRs, the phenomena of LENRs, people have been seeing this stuff for 125 years. So, and I want to give people a little bit of a historical perspective too, that I think might help. In 1831, Michael Faraday discovered magnetic induction, and he was an experimentalist. He found this. He found he could generate an electric current just by moving a magnet in a coil of wire. People thought he was nuts. He was pilloried by scientists, and he was nearly run out of the scientific community in England. Now, he wasn't, and he kept going, and then they started finding all these other effects. But the theory of electromagnetics that really tied all this stuff together wasn't developed until Maxwell came along in 1873. So that's 42 years. So sometimes there's a long gestation between a physical effect and when it's understood. Now, once it's understood, then commercialization can start. Now remember, Maxwell published Maxwell's equations effectively in 1873. 3 years later, Alexander Graham Bell patented the telephone. That's 1876. 1879, Thomas Edison patented the electric light. That's another 3 years, so that's 6 years. And then another 3 years, 9 years after Maxwell's equations were published, in 1882, Thomas Edison opened up the Pearl Street electric generation plant in New York City. And coincidentally, right around the same time, the first hydroelectric power plant opened in Appleton, Wisconsin. Well, everybody knows what happened after that. What I'm suggesting is that I'm not trying to puff us up or say that we're the equivalent of Maxwell. I'm not claiming that at all. What I'm saying is if our theory proves to be as useful as it looks to be, this can be what opens up commercialization in the same way.
Interesting.
Does that help?
Indeed. We are discussing Widom Larsen theory with Louis Larsen, low energy nuclear reactions. Okay, we're talking about the theory here and who's reviewed it. This is not pie in the sky stuff. This has been out for a few years now. It's had a lot of serious attention from the United States government, from NASA, and has pretty much been, the theory's been blessed in principle that the physics of it and it works. Have you had any interest from any foreign governments, or I know you mentioned that company overseas, but has other people been looking at this as well?
Oh, absolutely. There are people working on this in China, in Japan, in Russia, in Italy, in Israel, France. Oh, yeah. We're not the only ones.
Let me ask you a nice
by a long
question.
shot.
I don't know how this works, but did you patent this theory, or how does that work?
Well, you can't patent a theory, but you can patent embodiments, and we have patents filed and patents that have issued and patents pending, and you know, I'm sure there's going to be before this is all said and done, there'll be tens of thousands of patents in this field. I mean, it's a huge, rich area, and I truly believe the surface has only been scratched. It's sort of like you know, in whenever Sutter's Mill was in California, you know, they found the gold, and early on in the history of a week after Sutter found the gold by the mill, you know, you can walk up with gunny sacks, and as long as you can, you could find gold. So we've opened up, I hope, Sutter's Mill where other people can all start to find gold.
Louis, is the current United States administration aware of this?
Yes.
Current, okay. Okay. All right, well, let's move
what
on.
they decide to do about it is maybe another question, but yes, they are very much aware of it. I think to some degree there are various parts of the government that do believe this is real and that the physics are correct. But anywhere else, the government's a huge, big place with all kinds of fiefdoms and islands of this, and so it's hard to say. But yeah, A, we haven't received a dime in government funding, and B, they certainly know about this.
Okay, okay. Have you performed any practical lab tests with your theory in terms of generating energy?
We did. We ran research programs at a major university and a private laboratory for 3 or 4 years, starting in the beginning. This goes back to 2001 through 2003-04. What we did was, or I did as CEO, and I'm a theorist, I shut the experimental programs down because the parameter space is huge in this area, and unless you have the device physics worked out, you can wander around for another 20 years trying to figure out what buttons to push. And that's, in fact, what happened in the field. There wasn't a theory. People didn't understand the device physics. So people tried this and tried that and didn't really understand you needed to apply nanotechnology, which now we know, at least we know how to apply it if they don't, and really get things that are robust. Does that answer your question?
Yes, it does, Louis. Now, let's move back a sec here to this theory being reviewed by foreign companies, organizations, the U.S. government, and other governments. This undoubtedly would be a spanner, and a big one, thrown into the oil industry worldwide. What's your take on that?
Yes and no. Right now we're dependent on petroleum, especially in transportation applications. I mean, you can switch to coal, you can switch to nuclear, you can do a lot of things in power generation. But in transportation, because the internal combustion engine, in particular, since the majority of them in the world aren't diesels, which are more flexible, they're straight gasoline engines, you know, we're kind of held hostage to the oil industry. And I don't mean that in a terrible way. So if you're talking about a source that over the long haul, like I'm saying 20 or 30 years, could reduce the demand for oil, i.e. gasoline and transportation, yes. However, because of some very creative experimental work that was done in Japan by a fellow by the name of Dr. Tadahiko Mizuno at Hokkaido University, what now appears that you can trigger these LENRs in organic molecules, in fact, in benzene rings. And you can also trigger them on fullerenes. So that being the case, when you get these, they're called aromatics in fractions in oil, in theory, if this pans out and a lot more work needs to be done on the experimental side there, it could potentially be used as a nuclear fuel. So in one sense, it competes, and in another sense, we can use a lot less fuel because we can take part of what's now burned and burn it and release, 1 to 5 million times more energy. So it's sort of a two-sided question, two-sided answer.
Bottom line is, though, we're going to drastically reduce the amount of energy reserves and fuel that we draw on the planet to produce energy.
Absolutely.
That's what you're saying in simple terms.
Yes.
Okay. Lewis, I'm going to ask you a green type question here, green in relation to environmental. Does the mechanics of the Widom Larsen theory of creating energy, is it similar to what plants or any other life forms on Earth do? Maybe a ludicrous question, but I have to ask it,
Oddly, yes.
Really?
Yes.
Okay.
We don't talk about this much publicly, and you won't hear us say too much, but I will say this much publicly. If you think the last stuff's controversial, frankly, this is worse. But I will tell you something. There's experimental work that was done in Russia and elsewhere, and I happen to know the researchers that did it, and these are competent physicists and microbiologists. They know what they're doing, and they know how to measure isotopes. It appears that certain ancient types of bacteria, microorganisms, can do transmutations. Now, they don't do it for energy. They do it to create elements that they need that aren't present in the environment. So, yes. And there's evidence in the geochemical record for this. Up until now, geochemists say, they have this chemical fractionation process that they claim explains all these weird isotopes they see, and which is a logical explanation, but now that we've developed a theory, there's an alternative one. Now, what I can't talk about publicly is exactly what we know about this, but I will tell you this. If the experimental work is correct, and I think it is, and we didn't do it, other folks did it, but they're competent people, bacteria and some fungi can do this. So this is the ultimate green technology. I mean, the bacteria beat us by 2 or 3 billion years. If this isn't green, I don't know what is.
And also might be green in color, some of it anyway, right?
Well, what's amazing is and not only that, but there's recent research on what they call the absorption centers in photosynthesis, where they call them the antennae. And although nuclear reactions don't take place in there, oddly enough, I've looked at and talked to some chemists who are working on this, the same types of collective phenomena that make nuclear reactions possible are involved in the absorption of antennae and photosynthesis. So these collective effects in these many body things run throughout nature.
Lewis, when you talk about...
But you just don't see them because they don't produce a lot of radioactivity. Isotopes are nasty stuff.
Indeed, indeed. When you talk about transmutation, can you explain a little bit what that means?
What transmutation means is you take an isotope. Now, some elements are more than one isotope, and all that means is you got a different number of neutrons but the same number of protons, and you somehow either change it to another isotope of the same element or a totally different element. One of the ways you can do this is with neutrons, and that's what the ultra-low momentum neutrons do. They're absorbed locally by, these different nuclei compete to absorb these things, and you make different things. Now, when a nucleus absorbs one of these ultra-low momentum neutrons, sometimes it's stable and you just get a stable isotope. Other times it's unstable. When it decays via what's called beta decay, and all that is you release a neutrino, an energetic electron, and sometimes you release a gamma. But the gammas in these systems get converted to infrared by the heavy electrons. The neutrino just flies off into space. And the electrons, as you pointed out in the beginning of the conversation, you can stop those with a piece of paper or skin. So you see new isotopes, but you don't see radiation. And when you do that, when you do these transmutations, you release nuclear binding energy. And you can release nuclear binding energy from almost anything. So there are all kinds of fuels. You can make the neutrons. The different fuels you can use are infinite. So right now where we can only use uranium, and there's some in fission reactors and some talk about thorium-based reactors and uranium-233-based things. With this technology, the fuel sources effectively are ubiquitous. Some are just better than others. So there wouldn't be any shortage of fuel, but it does cost energy to make these neutrons. Now, to make one of these neutrons, depending on whether you're using deuterium or hydrogen, either costs anywhere between, let's say, 0.78 mega electron volts down to 0.39. Because in the case of deuterium, you get 2 neutrons for the energetic price of 1. Now, when you release nuclear binding energy, let's say typically if you're, say, absorbed by nickel, just absorb a neutron. That'll release around 5 MeVs. That's just what they call the curve of binding energy. So what happens there is you lose some of it in neutrinos, which you can't capture, but some of it is converted to energetic particles, like alpha particles or beta particles, which are electrons and helium nuclei that bang into the material, heat it up, and gammas that get converted. So you're basically using neutrons as a match. Now, the energy was stored in these nuclei billions of years ago when they were formed as stars. In the same way you can take a pile of wood 60 feet high and you've got the right kindling down below, you could take one match and light the whole thing on fire. That's how these neutrons work.
Lewis, we have a question from the chat room here. It says this is the first time I've heard about transmutations in regards to isotopes, but the question is, I'd like to know why this information is being withheld, meaning your theory. I don't know if it's a case of being withheld, but what's your take on that?
Oh, it's not being withheld. I'd say in many quarters it's being ignored.
Ignored.
It's well published. I mean, we've published this stuff all over the world. Now, as far as the core of it, there may be a lot of people that don't really understand it. I mean, even some physicists have a tough go of it because it's so interdisciplinary. But do I think there's any kind of conspiracy against this? No. No. Do I think that there's a lot of difficulty maybe to understand what we've done and the fact that it breaks a number of different paradigms? Yes. Thomas Kuhn wrote a book about this, The Structure of Scientific Revolutions. And whenever you have a paradigm change, there's huge resistance. And maybe that's just humanity's, maybe if human beings were too receptive to new ideas, maybe there'd be too much chaos. So the answer is it's a combination of ignorance and people that don't want to deal with it. Well, does that answer the question?
Yes, it does. Thank you, Lewis. We all talk about change. We all preach change. And yet, when change comes to us and we're asked to stand up and deliver, most of us choke. Because as human beings, we don't like change. We want certainty. We want to know the price of gas on Monday morning. We want to know what the US dollar is going to be next Wednesday. We want to guess the unemployment rate by next Friday, correct? So change and unpredictability are not in the human nature. We all strive to be these pioneers and embrace change and move on to new things, but when that change is often presented to us, we quite literally, as a species, Lewis, choke.
I agree.
And when we review history, we congratulate ourselves on our innovative changes and everything else we've done. But when true change comes along that can affect the whole planet and humanity as a whole, well, I'm not too sure about that. Let's just make it so it just benefits us or the selected few. So some people might scold me for that, saying, well, that's business and that's how countries and territories work. Hey, all I'm saying is just review history, and here we have this theory that's just moving on from a theory to a working theory that's on the verge of being a prototype, which according to some highly credible sources here in the U.S., i.e. NASA, for one, has blessed this. It can give us clean nuclear energy, and I mean clean, draw less resources from the planet, and give us a very low cost of energy, not only here in North America, but elsewhere, and really change the world. So the question is, what's wrong with this?
Well, yeah, there are people that have looked at our theory that have said, well, it's got to be wrong. It's too good to be true. Well, sometimes things aren't too good to be true. Sometimes they're just there and real and just unexploited. And that's the way I would characterize this. It's unexploited.
Okay, well, it needs to get exploited, Lewis. Good old-fashioned human way. In human ways, let's say, because once you start the trickle, the torrent and the floodgates will open. Okay.
Well, that certainly happened in the 1880s.
Yeah. Hey, on this, talking about way back when, did any of these scientists at that time ever kind of touch on this a little bit? Did any of them ever look at this, some of the early pioneers of electricity? And
absolutely they did. It's incredible. I could show you papers, in fact, they're referenced in one of our slideshow presentations, back around 1901, 1902, 1903, where these are the top guys in British science, Ramsay, Thomson, who discovered the electron. They were doing these experiments with electric discharges of large current electric discharges in gases. And they didn't have mass spectrographs like we have today, but they were pretty good with spectroscopy and seeing lines of elements in hot gases. And they were seeing transmutations, and they couldn't understand them. But in 1905, Einstein came out with his paper, just kind of, 3 paradigm shifts right there, and then quantum mechanics got started up, and because people couldn't explain this, they just kind of dropped it. It surfaced again in 1922, right here at the University of Chicago. What these guys did is they blew up a wire in an evacuated flask, they call it. These guys are named Wendt and Urian, and they saw helium. They saw transmutation. So somewhat similar to Pons and Fleischmann, they reported this at an American Chemical Society meeting in Evanston. The news wires picked it up, and this is in 1922. It gets spread all over the world, all over the New York Times, London Times, transmutations. Well, the establishment, the scientific community, decided they didn't really like this because it didn't match theory, so Rutherford comes up and writes a scathing attack on these guys in Nature. Well, here are these 2 chemists at the University of Chicago, Wendt and Urian, and you've got Rutherford, who was a giant of science. He effectively destroyed their careers. We went back and analyzed their data and with our theory, and guess what? Rutherford was dead wrong. These guys were dead right. Well, a few years after they published this, Wendt dies, and Urian went to teach chemistry at a little college in Iowa. So it was forgotten. It was rediscovered in the early 50s at Cornell University, and that time Bethe, the legendary Hans Bethe, and Einstein even got involved. They had some experiments they couldn't explain. The kid was working on his PhD. Well, Einstein said, gee, I think this could be collective effects. Well, the fellow wanted to get his PhD. Nobody could figure it out, so they dropped it.
Yeah.
So it's happened time and again. People have seen this, and for one reason or another, it got dropped. So this has been going on for 125 years.
Okay, so we got to a point now where your company has put together this theory that explains this more clearly, so we start to get our arms around it. So it's starting to make some type of sense, so we don't get confused and drop it again. Right. What's the next step for Lattice Energy?
Well, for us, we've got to raise the amount of funding we need, which is significant, to do the engineering prototypes. We think that will take 2 or 3 years. If we get through that phase successfully, then what we will have demonstrated is that devices that work reliably, are robust, and can ultimately develop into commercial products. And now if we get through that phase successfully, and then of course you got to raise more money if you get through that okay and get past that milestone, then we're probably talking, I would say, realistically 4 or 5 years to a commercial product. And that's something, I'll define a commercial product, somewhere between 5 or 10 watts and up to maybe 5 to 10 kilowatts. Engineering-wise, it might be easier to do a larger product first. But once that happens, then it's sort of like, you know, the PCs really started out in 1979, 80, 81. It took 30 years, but you see what happens. So I would say if that phase is successful, within 30 years, if it's a similar kind of development path, you'll see a collapse in the effective price of energy.
Okay, so we got about 3 years in for a prototype, and then we start moving into commercial applications. Yeah. Well, that's not a long window at all. So it may sound long to some, but it's not. That in scientific terms, that's not at all. So you're not too far away. Well, I'm sure with the amount of interest you're generating, and just by logically and rationally looking at your work and who's reviewed it and who's interested in it now, that next prototype stage shouldn't be too far away. And again, I'll repeat this for about the 4th time. We're talking about a theory here that's going to be able to provide the people of this planet with a form of nuclear energy that's safe and clean. It's going to be very cheap in the long run, and it's going to draw far, far, far less resources on the planet. And then to reiterate point number 1, it's not going to poison the air, which everyone's all hot and heavy about right now. So, looking at this from a logical perspective, why wouldn't the people of this earth jump all over this like an army of ants? I see no reason why not. I mean,
I'm waiting.
The choice is, Lewis, do we move forward on a scientific level or do we remain in the caves? Because this is what this is like. What you're telling us now is like going from the caveman in the fire to where we are right now. So this is the same leap. We can either stay in the caves or we can go out to a brand new world that's going to benefit us all. And by the way, we're not talking about wrecking the energy industry. We're talking about changing it for the better of all, which change always leads to more opportunities in the commercial world. It does.
Yes.
It does. IBM were the only guys who came out with a computer way back when. Well, at least on a main scale, right? And then all of a sudden, every Tom, Dick, and Harry's involved. How many companies have been born out of the computer industry? How many software jobs have been created? How many support jobs are being created? How many products are sold in stores? How many people work in them stores to sell them computers? Lewis?
Oh, well, the computer industry, I think, is just machines are $125 billion a year from nothing 30 years ago.
There you go, from nothing. So this could mushroom into a whole bunch of economic activity for everything. And if it's going to better the people of the earth, then surely, why? We have to get a cap on energy. We have to keep drawing the resources that we're doing with the planet right now, and it's just absolutely insane. Okay.
I agree.
Let me ask you one final question on a personal note. Why are you doing this? Why are you doing this? Putting your
oddly, it's only partly the reason. Money is only part of the reason. I'm sure that's part of it, but that's sort of what's something you get at the end. I'm doing this because I think this is important. I mean, I'm 63 years old. I'm a decent physicist and a decent businessman, I can't think of anything more significant that I could do with the rest of my life than to help make this a success. And I say, and I use here the collective we. This is way bigger than Lattice. This is way bigger than IBM. It's way bigger than the United States. This is just the beginning, in my opinion. So I'm doing this because, you know, if we can, you know, draw our last breath, leaving the world a little bit better place than the one we came into, we did all right.
Exactly, exactly. Brilliant. Well said. It doesn't matter how much is in your 401k when you leave. It's what you did when you were here before you leave.
You can't take it with you.
No, you cannot take money with you, and that, Lewis, is a scientific fact, and we'll challenge anyone to come on the show and dispute otherwise. Okay? So now, what's your last thought? What would you like to leave the audience with?
What I'd like to leave the audience with is, well, it's really it's something that came out of a book by Thomas Friedman, 2008, Hot, Flat, and Crowded. It's actually, I think Tom did a takeoff on Archimedes, who said, "Give me a lever and a place to stand and I can move the world." Here's what Tom Friedman said. "No single solution will defuse more of the energy climate era's problems at once than the invention of a source of abundant, clean, reliable, and cheap electrons. Give me those electrons, and I will give you a world that can continue to grow without triggering unmanageable climate change. I will give you water in the desert from a deep generator-powered well and put every petro-dictator out of business. I will end deforestation from communities desperate for fuel and eliminate any reason to drill in Mother Nature's environmental cathedrals. And I will enable millions of the Earth's poor to get connected, to refrigerate their medicine, to educate their women, and to light up their nights." Thanks, Sandy, for inviting me on your show. I mean, I really enjoyed this. I think shows like this are very important because they bring science and the people closer together. And I'd like to thank the audience for listening in today. And just remember one thing. If scientists can't explain their science in plain English, they probably don't understand it very well. So don't be afraid to hit the search engine, study the information, form your own opinions on science issues. That's the beauty of the Internet. It democratizes access to information, and we want to democratize access to affordable energy. That's why Lattice is here.
And further to Lewis's comments there, if you look on the main page of the Universal Learning Series website, and the same information will be on the archive section, there's 2 web links, 2. Normally there's 1. On this segment we have 2 that provides you with web pages that you can view the theory in more detail. And also, one of the links has a very nice conversational tone to it, where Lewis responds to questions, comments regarding the Widom Larsen theory. Lewis, thank you very much for coming on to the show here.
Thank you.
And I wish you all the very best, and I'm sure we'll be having you on again.
Thank you so much. I really enjoyed it, and I hope your audience did too.
All right. Thanks, Lewis. Have a great day.
You too. Thanks. Bye-bye.
Bye. Well, that was Lewis Larsen, the president of Lattice Energy LLC. Widom Larsen theory, low-energy nuclear reactions. Interesting stuff. Can it change the world? Maybe a strong possibility. We'll see. Well, thank you for listening to the Universal Learning Series radio show, where we discover the spiritual and scientific universe.